Please. We don't have any fire alarms planned, any drills, I should say, planned for the afternoon. So if you do hear the fire alarm going off, it's the real thing. And if you're sitting at the front of the auditorium here, your fire exit is out through that door. Obviously, follow the green illuminated sign, and you'll find yourselves outside in the Burlington House courtyard. For those of you who are right at the back, you can exit through any of the three doors at the back of the building and out through the main reception, onto Piccadilly, and again, if you muster in the courtyard out there, please. Just one other thing to say, if any of you do have mobile phones, well, which is probably all of you, would you please make sure that they're turned off so that they don't interrupt the proceedings this afternoon? Thank you. And so now on to the afternoon's main bill. So welcome to the Geological Society of London, to this, the 7th public lecture of 2017, which is entitled, Not Under My Backyard, Are Public Perceptions of the Risk of Geological Engineering Projects Well-Founded? I'm Richard Hughes. I'm the Executive Secretary here at the Geological Society in London, and it's my pleasure to welcome this afternoon's speaker, Zoe Shipton. A little bit about the background to Zoe's talk. Modern society is crucially underpinned by the use of geological resources that include minerals, metals, hydrocarbons, and so on, groundwater. We put our subsurface infrastructure, such as sewerage, transport tunnels, crossrail, and all sorts of things beneath the ground, and of course, waste disposal. And there's been a lot of recent high-profile media coverage of a range of geological engineering risks associated with, for example, fracking for shale gas, wastewater disposal, and radioactive waste disposal. Interestingly, research finds that the perception of risk differs very greatly between the public on the one hand and the technical experts on the other hand. So what's the source of this discrepancy? And what can the engineering and geoscience professional communities do to better address or take on board public concerns and to understand them and respond to them? Professor Zoe Shipton is Head of Departments of Civil and Environmental Engineering at the University of Strathclyde, where she researches the architecture of fault systems and related permeability issues. In 2016, she was elected a Fellow of the Royal Society of Edinburgh, having in 2010 been awarded this society, the Geological Society of London's William Smith Fund, for excellence in contributions to applied and economic geology by a researcher under the age of 40. So, ladies and gentlemen, would you join me in welcoming Zoe to the lectern, please?
Thank you very much, Richard. I'm just going to get some water. So I was rather proud of this pun. So I've been working with social scientists recently, and social scientists love putting puns in the title of their papers. So well-founded is a deliberate pun on things being deep. And before I move on, I want to thank not really co-authors. None of these people are responsible for any of the content of this talk. These are all my ideas and opinions. But they are definitely responsible for helping me think about these issues. So Jen Roberts in particular is a postdoc working with me, and Chris Ford is a PhD student. He's a brilliant PhD student. He's a retired town planner who's doing a PhD for fun. And as Richard said, there have been a lot of very high-profile discussions in media for recent times about these apparently controversial techniques that use the subsurface. But we use the subsurface all the time, and none of you in this room are free of products that came from the subsurface. If you're wearing something that's made of plastic, you are wearing something that's made of oil and gas. If you're wearing cotton, that was almost certainly irrigated by some form of groundwater. So the subsurface resources that we use are absolutely interwoven with our everyday lives. Before I move on, this is the GeolSoc's Year of Risk, and I wanted to have a think about the technical definition of risk. So risk is the hazard that something poses multiplied by its likelihood. So the risk that I might die in a car accident is relatively low because car accidents don't happen to individual people that often. But the risk that so this is a diagram here showing perceived risk and actual risk. So on the top is what people feel. They think that car accidents aren't very likely to happen, but actually they're much more likely to happen than something like a plane crash. So, but I've never met anyone who had to be talked down out of a panic to get into a car, right? So plane crashes, if it happens, you're almost certainly dead, but they very rarely happen. Whereas a car crash, you can survive a car crash, and car manufacturers have put all sorts of safety methods in, you know, safety belts and roll bars and all sorts of things. And local authorities try and mark up roads to make people drive more safely. And we have laws about things like drink driving. But this is a really fascinating diagram to me because it illustrates the difference between actual technical risk, so the hazard of something happening to you multiplied by the likelihood, and the perceived risk. And later in this talk, I'll present a different equation that's been proposed by some social scientists for how we should calculate perceived risk. So now I'm going to indulge you a bit and show you some of my holiday photos from my most recent bit of fieldwork. Can you see this all right? We might need to turn the lights down in the auditorium if that's possible. No? Okay. So you'll have to bear with me on this slightly dark picture. So this is a photograph taken from the top of the Grimsel Pass. And Grimsel is a very famous road if you're into motorbiking or cycling. It's one of these fantastic winding alpine passes. And it winds up through, look at this beautiful, pristine alpine landscape, right? This is a kind of an epitome of a not messed around with sort of beautiful wilderness, except it isn't. So first of all, this structure here that's just sneaking out around there, there's the Grimsel Hospice, an incredibly, fantastically expensive hotel, very beautiful. And it sits right on top of two huge dams that were started in the 1920s. And these things are phenomenally high concrete dams. And those dams dam this lake here, which is Grimselsee, and there's a younger dam down here that dams Radioactive. And this is part of a system of dams that supplies electricity to 1.2 million people in Switzerland. There are tunnels all the way through these mountains. And in fact, this cascade here that suddenly pops out the side of the mountain is supplying the Grimselsee with water from another lake behind that ridge. So although this looks like a pristine wilderness, it is in fact a giant electricity generation system. It's pumped storage power station. So when electricity is cheap, they pump the water back up into the lake. And when they need the electricity, they turn on the turbines. The water rushes down through the dams and generates electricity. So this is a beautiful example of geological engineering. Here's a map just to show you this. That's Grimselsee, Radioactive, and this is a huge, complicated network of tunnels underneath the rocks that connect together all of these lakes. I think there are 8 dams, 9 power plants, between 2 and 2,500 gigawatts of electricity every year. So it's a phenomenal amount of electricity. So another thing that's underneath this landscape is the transit gas pipeline. Now this gas pipeline takes gas from Northern Europe across the Alps and into Italy. And it has to cross 3 of the big mountain passes in the Alps. Phenomenal bit of engineering. And this is all tunnelled. So you can see here the tunnels, you can see the gas pipeline. There's a little railway thing here to get engineers up and down for checking leaks. But this runs right the way down through Grimsel Pass. And then there's a map of these things. This is Grimsel Pass here. This incredible tunnel goes up and over these passes. It's one a bit like it in the Lake District. If you ever go walking up the pass just east of Patterdale, there's all these weird concrete boxes at the top, and that's a big water pipeline that's transmitting water for drinking water. So the other bit of really interesting infrastructure is the Grimsel test site. In the next slide, I'll show you where that is. But the Grimsel test site is one of the 2 underground research labs that the Swiss Nuclear Agency have set up. The idea is that when they set these 2 research stations up, they hadn't decided where they were going to put their nuclear waste. So they set one up in granite, which is what these mountains are made of, and another one in clay-rich rock. And they've now decided they're going to put their waste in clay-rich rock, which was examined in the Monterey site, the Grimsel site in granite is still open because there's a lot of interesting research you can do on the engineering without having the geology right. So you can put things there and leave them for a long time and check what happens when the engineered part of a geological waste disposal sits underground for a long time. And this is one of my ex-PhD students who is measuring groundwater chemistry. And this is a complete aside. This has nothing to do with the rest of this talk, but I can't avoid saying it because it's so cool. But in 2015, the water company drained that lake. So this is a view from that dam looking back up in this direction. They drained the lake, they pulled the plug because they put a new power race through the dam. And the team of PhD students are working in the Grimsel test site, which is underneath this mountainside here. It kind of runs along there, monitoring the groundwater chemistry and with very, very, very sensitive seismic sensors, monitoring the tiny earthquakes that the rocks make as they go, oh, there's no lake on top of me. And then, oh, there is a lake on top of me. And the reason that we're doing this is we're trying to understand the really large-scale stress changes when glaciers go over rocks, but not very much to do with public understanding of geology, but just too cool not to mention. So, this is an example of geological engineering under the landscape. And here's another one. This is a road I cycle along every day to work. It's Titwood Road, just on the south side of Glasgow. Looks like your average sort of urban street in Glasgow. But underneath Titwood Road, and I'm not quite sure how far down it's got yet, is this thing. This is a Herrenknecht tunnel boring machine. It's similar to the one that did the tunnels at Crossrail. And if you get off the DLR station at Cutty Sark, they've actually painted some of these bits from the TBMs that cut the DLR under the Thames and painted them red, white and blue at the Cutty Sark. These are absolutely phenomenal pieces of kit. This is 4 metres in diameter. That tunnel would be big enough to drive a double-decker bus through, and they're driving it right underneath Titwood Road. Between the Bellehouston Park, which has the House for an Art Lover in it, one of Rennie Mackintosh's houses, underneath Pollock Park, which is Europe's largest inner-city park, along to here, which is Queen's Park, where it will connect with the existing sewer network to take wastewater, floodwater and sewage away. And interestingly, I live quite close to this place. We've had Scottish Water putting leaflets through our door telling us about road closures, but there haven't been any protests. I did a bit of searching around on the web to see if I could find anybody unhappy about the Shield Hall Tunnel, and I couldn't, but I did find lots of amazing pictures. So, yeah, just to give a sense of scale, you know, again, here's where the portal, it's called, where the TBM is going to push its way out of the rocks into a big hole like this, which is going to be the kind of the receiving station for that tunnel. Now, one thing that has had to happen at our local railway station, which is called Crossmaloof, there are mines underground, abandoned mines, and they've had to put grout in those mines, basically slightly runny concrete that they pump in to fill up the cavities before the TBM goes through. And that closed that intersection. It didn't close the intersection. It made the intersection difficult to get to for 6 months. But again, nobody's there going, we hate the Shield Hall Tunnel. You know, people are very interested in well, they're either completely not interested or they're very interested and positive about it. You know, this is going to help with flood remediation and not having sewage coming up into people's houses during floods. So contrast these two sort of images of very positive experiences of underground geological stuff with the next three technologies. So this is a picture of the front cover of an International Energy Agency book about carbon capture and storage. So carbon capture and storage, you've all bothered to come along to a GeolSoc lecture on a rainy afternoon, so I'm going to assume a certain level of geological knowledge, but I will, you know, hopefully I don't bore you, but CCS is basically the idea is you take the carbon dioxide produced from point sources, mainly power stations, but you can also take it from industrial point sources like cement factories. You compress it, transport it in a pipeline, and stick it underground. And interestingly, contrast these two images. This is the International Energy Agency's image. So it's got a sort of Google Earth style photograph of a facility, and it's true to, well, it's not quite true to scale because you can see these wells. If it was true to scale, they'd be like tiny, tiny hair thin things. But they've attempted to show you quite how deep underground this stuff has to go. It has to go at least 800 metres underground, because at depths below 800 metres it changes phase into a supercritical phase, which makes it much more stable. But quite possibly they'll be putting it much further underground than that. But contrast this with the Wikipedia page I searched yesterday. And it's kind of weird. This tower here, this sort of flue stack from the hypothetical power station, is about the same depth, maybe slightly taller than the depth of these weird black lines going into these strange wobbly triangles. It gives the impression that this stuff's happening right underneath our feet. But carbon capture and storage is not a mature technology. We have done it in a few places, sort of. So we've been commercially sticking CO2 under the ground for a long time. We use it as a sweep fluid to push oil and gas out of oil and gas fields. It's called enhanced oil recovery. So we do know quite a lot about how to handle CO2 safely in pipelines and on facilities. And of course we use it in food manufacturing. So there's been a number of research projects around CCS. Weyburn in Canada is an enhanced oil recovery site where they instrumented it up to get extra data about what happens to the CO2. The Norwegians have been injecting CO2 into the North Sea at a place called Sleipner. And there's a number of places around the world, Otway in Australia and so on, where they've been trying to do this. And the world's first fully commercial CCS project is at Boundary Dam in Canada, where they're taking CO2 out of a coal-fired power station and injecting it deep underground at the bottom of the Williston Basin, which is interestingly the same basin that quite a lot of the US shale, US and Canadian shale, is coming out of. Those commercial sites have had no real health and safety problem. I mean, every commercial site, has health and safety problems. The Jolsop probably has people falling over every so often that you have to do first aid on. That kind of thing, I'm sure, has happened. But there haven't been any kind of high-profile disasters. There haven't been any incidences of felt seismicity from CCS, and there haven't been any uncontrolled releases of CO2. There have been one or two deliberate releases, and there was a brilliant study done on the northwest coast of Scotland where they piped CO2 just offshore, buried the pipe in the sediment underneath the seabed, and turned it on to let the CO2 dribble out, to look at how that CO2 leaking in the seabed might affect the marine life. And there's an absolutely fantastic video of a crab going over to a bubble stream, and it kind of does this. It doesn't really care. But it does have, it's CO2, it changes the pH, and it does stuff to the chemistry and therefore the ecology. But despite this, there have been big protests in places where CO2 storage has been mooted, particularly in Germany and in Holland. And I love this picture here of a catastrophic blowout of CO2. It's about to take out this helicopter. It's real Hollywood movie stuff. But both of the projects in Germany and the Netherlands didn't take place in the end because of these public objections. Okay, Richard referred to geological disposal, and I referred to it with the Grimsel test site. So the concept of geological disposal is that we've been irresponsible enough to make this stuff that's going to be poisonous, toxic, radioactive for tens to hundreds of thousands of years. Most of it is currently all of it's currently sitting in various safe storage facilities above the ground. We can put our low-level waste below ground. We produce low-level waste in hospitals, for instance, in X-ray labs, in research labs. That goes underground into a low-level waste storage. But the high-level waste we need to have a solution for. And that solution's got to last for 10 to 100,000 years. Now, the longest civilization on Earth was the ancient Egyptians at 3,500 years, and then they kind of went belly up. So the people who are designing these things have to design for all sorts of kind of Mad Max-style futures where society has collapsed, or we've been invaded by aliens, or we've been taken over by super-intelligent cockroaches. And I kid you not, there is an absolutely brilliant film about this called Into Eternity. You can download it off the web. You have to pay the guy. It's well worth watching. And he talks to the Finnish nuclear agency's theologist. And they employ a theologist to think about the moral issues around how do you do this? Do you signpost it? Do you say, don't drill here? Because if you do that, then some future Indiana Jones is going to turn up And it didn't put Indiana Jones off having all those skeletons jumping out at him from these places. But if you don't flag it, and the super intelligent cockroaches get out their Geiger counters and they're looking for fuel for their nuclear power stations, they might start digging and get a nasty surprise. So there's some really, really interesting stuff around radioactive waste disposal. It is not just the geology. It will be tunnels and shafts that have engineered barriers in, and a huge amount of research is going on around the engineered barrier, as well as thinking about where would be a good place to put the geology. Where would be a good place geologically to put the waste, sorry. And the answer to that really is somewhere that doesn't change very much. So engineered things don't like change. Okay, cars don't like it when you put salt on the roads in the winter and they rust. So, and that would be the same for the engineered barrier. If the salinity changes, then components in that engineered barrier might start reacting and changing. So what the Finns have done, and this is a model from the BBC of the Finnish kind of concept, the Finns have put their waste in the middle of really, really ancient cratonic rocks. Nothing much has happened to for for millions of years. A few ice sheets have gone over now and then, and that's why we're mucking around in Grimsel monitoring groundwater. But not an awful lot has happened. And tectonically, we can kind of we can look at the plates and say, well, nothing much is going to happen to this place. So it's going to be stable and keep those engineered systems stable. We're currently in the process in the UK of trying to site a deep disposal site for the UK. It's against international law to ship it across the sea. So all waste produced in the UK has to stay in the UK. And so we do need to find a solution for our waste. And leaving it on the surface is an option. But we do have to remember that it's got to last for 10 to 100,000 years. And we can't have future generations of super intelligent cockroach teenagers jumping over the fence and nicking plutonium or whatever. So the UK government has decided to go for deep geological disposal. And we're now in the third round of trying to find a site. The first round failed in the 1990s. It failed at planning. The second round failed just a few years ago because they decided to go for a volunteerism approach, which is what they've done in Finland and Sweden. They've asked communities to volunteer to host the site. Now, in Finland and Sweden, the communities were falling all over themselves to host this site. This was going to bring in jobs and infrastructure to these communities, remote rural communities, for hundreds of years. So when they decide a site, they're going to have to do a whole bunch of baseline data collection, which means bringing in geologists and geotechnical engineers and drillers. They'll need B&Bs and they'll need restaurants to go and eat in and so on. Then they'll build the site. There'll be a whole phase of construction work. And building that site will involve surface facilities, access tunnels, and then a whole range of waste storage tunnels in different configurations for depending on what kind of waste it is. And then once it's finished, the estimate is it will take 150 years to put the UK's current high-level waste inventory into that waste disposal site. So these communities in Finland and Sweden wanted this. And a few years ago, they went through a process of asking for volunteer communities. 2 communities came forward, had local referenda, and said, yes, we're willing to go to the next step. Now, going to the next step means talking about whether you really are a good site or not. But the regional council said no. So Copeland and Allerdale voted that they would be interested to talk about it, and Cumbria, the regional council, said no. And again, there's all, if you do a quick Google about radioactive waste, you'll find all sorts of discussion in the media. My least favoured term is dump. When people talk about radioactive waste, dump. I mean, dump is something you do with dumper trucks, right? You kind of go beep, beep, beep backwards and then tip it up and tip it in a hole. This is not what a radioactive waste site is going to be. It will be highly engineered and sophisticated. But we still haven't got one because of all this public uncertainty and unease and controversy. And then finally, the one that's really hit the media in the last few years is shale gas. And people, it's really interesting. I've watched this very closely since about 2011. And the narrative around this, the words that people use have really changed through time. People used to say it's a new technique. Well, it's not a new technique. We've been using it in the UK since the 1950s offshore. It's a technique where we pump high-pressure water down a well until that water can overcome the stress on the rock and crack it. And you can do this in the safety of your own home by sticking a straw in some jelly and blowing. And you will frack that jelly. That is essentially what's happening. Now, if you do it in an uncontrolled way, jelly will end up all over your kitchen. But you can do it slowly and gently propagate fractures through your jelly. People say it's an unproven technique. Well, like I say, we've been doing it in the UK since the 50s. People say that onshore gas and oil is new. Well, that's not true either. And these are 2,000 wells for onshore oil and gas in the UK. There's one down here in Witch Farm. Has anyone been to the Witch Farm oil field? Yeah. What's it look like?
It's just got a nodding donkey thing going back and forth.
It's nothing. I mean, but it was the world's longest horizontally drilled well until the Russians beat us. It's 11 kilometres long offshore into the Poole Harbour area. So the idea with shale gas is you will drill down into rocks that contain gas that's so tightly bound to the rock that it won't come out otherwise. And you, rather than drilling vertical wells, you drill horizontal wells, and that basically gives you a bigger volume of rock for your surface facility. And then you would frack those shales, drop the pressure down, pump the water out, and then comes the gas. Now, remember that Wikipedia image of carbon capture and storage that I didn't like? Well, I don't like an awful lot of images of shale gas either, because they give you the impression that either the rigs are 2 kilometres tall or we're fracking right below our feet. And this is one that I drew to scale. Thanks to one of my old PhD students, I copied the idea off an image he did for geothermal energy. And he is now working at Glasgow University, and I couldn't possibly put Glasgow University for scale as he had, so I put the Forth Road Bridge. So here's the Forth Road Bridge, rail bridge, sorry. This is the typical depth of shale resources in Scotland, not very dissimilar from shale resources in England. And because the report we were working on also included coal bed methane, which is a different way of getting gas out of coal rather than shale, the coal resources in Scotland are a bit shallower. And also for scale, I very carefully, this is the drilling rig. That's the height of a fracking rig to scale with the depth of the rocks and the Forth Rail Bridge. What's not to scale is the wells. The wells on this would be thinner than you could see because the wells are about 10 centimetres in diameter. So it's not a new technology. We've used horizontal drilling at the Witch Farm oil field for a very long time, for decades. We've been fracking for decades, and yet this huge hoo-ha came about. It was really kicked off and escalated by the earthquakes that happened in Lancashire in 2011. And they were the first, at the time, they were the first earthquakes to definitely be associated with fracking rather than other activity. So we know we can trigger earthquakes by filling dams, for instance, or injecting wastewater. But these were the first in the world to be definitively linked to fracking. But they were a magnitude 2.3. Now, in central London, the BGS can't pick up a magnitude 2.3 because the background vibration from all the buses and pile drivers and the other stuff that happens in cities, they really need to go to the countryside to be able to feel earthquakes that are that small. But this happened in the countryside, and it happened fairly close to people's houses, and they felt those earthquakes. And it's pretty, I have to say, I've slept through 3 earthquakes. I've never actually been awake through an earthquake, but I have been to the Natural History Museum's little earthquake shaky table thing. It frightened the bejesus out of my kids. My daughter won't go on it. She's absolutely terrified by it, and that's just a pretend one. So people were concerned, and there had already been a kind of rumbling of discontent around fracking that was drifting over from the States, and it really escalated. And now we have big protests, we have people chaining themselves to sites, we have judicial review of planning applications going in. It's caused huge controversy. So, for the next bit of the talk, I want to just go through why I think this controversy has happened for geological engineering projects. And I've got a number of answers to the question, not all of which are true, or they're true to some degree, and it's such a complicated issue. But The first one, the one that most academic geologists and many industry geologists seem to think, is it's just because they, the general public, they just don't understand the geology or the technique. Now, I've nicked these photos off the internet. This is where a lot of people learn about geology, from films like The Core and Dante's Peak. I don't know if anyone's seen The Core. It's absolutely brilliant. I laughed so hard that my stomach hurt, and everyone in the cinema hated me. And my geology friend were there, and our two boyfriends at the time were like, "Why is that funny?" That was a diamond. There's a geode with silica in it in the mantle. Oh, doesn't work geochemically. You know, it's wrong for so many reasons. But it's, you know, it's a disaster movie. It's a bit of fun. But if that's your experience of geology, earthquake 10.5 is another. It's dreadful, low production values. A 10.5 earthquake, somebody once told me, would split the earth in half. But in this movie, it just slides California off into the sea in a really kind of, it looks like somebody's cut it with scissors and then shifted it. It's not a good, it's not as fun as The Core. Anyway, so are people rejecting these geological engineering things because they don't understand the geology? Oh, I keep pressing the wrong button. So there's Ian Stewart, you may all have heard of, you may even seen him talk. He probably talked here a number of times. He's the guy who makes the fantastic TV programmes about geology. And Ian has a wonderful postdoc called Hazel Gibson, and they've been working together on what do people think is down there. If you ask people what they think is underground. And Hazel came up with this brilliant experiment where she had a block, a 3D block with paper on four sides and a kind of a printout of some landscape on the top. And she asked people to draw what they thought was down there. And the top two images are of experts, and that kind of, you know, any geologist in the room will say, well, that's a granite intrusion. So, you know, clearly as he thought about, you know, the hills here being underlain by granite, that seems very plausible. But some of these non-experts actually thought that there'd be houses and buildings and stuff underground. You know, well, but there are in James Bond movies, right? You know, so if that's your experience of the subsurface, that's kind of legitimate. So people have these images of what's in the subsurface that's wrong. And one of my collaborators that was on the front page, we'd been working together on issues around fracking for 6 months before she'd said to me, so oil doesn't come out of big holes in the ground then? And she had honestly thought, she's a competent academic, she's not a geologist, and she had thought that wells found rooms like this big full of oil, and they were searching around and found it and then tapped it off. She had no idea that the oil came from the holes in between grains of sand in a sandstone. So, you know, if somebody very well educated and engaged enough in the subject to have been researching it for 6 months has an incorrect idea of the geology, then yeah, maybe that's where people are getting the idea of the risks from. Sometimes it's almost impossible not to laugh. And I see you laughing. This is an article from This is Somerset magazine or newspaper, and it says, Somerset experts suggest that if we drill into the Mendips, we'll trigger a volcano. And I love this. It may sound ridiculous, but it's no more ridiculous than drilling deep into the Earth's crust and setting off explosions. We could be sitting on a volcano. You know, could be holding back a river of lava. Now, there is lava under the Mendips, but it's hundreds of thousands of years old. But, you know, all credit to the guy to actually digging around, to getting involved enough to dig about and start trying to understand what's going on. But it takes undergraduates a long time to get to the point where they understand the difference between lava that's coming out of a modern volcano and ancient lava. And I've stood with undergraduates on the Isle of Arran, where we have, you know, hundreds of millions of year-old lavas that are all dipping sideways. And he said, where's the volcano? Well, we don't know. There's no, you know, the lava may have flown from up. How did it go from up there? Well, everything tilted. And this was at the end of the first year of a degree studying geology. So when I first read this, I laughed in a kind of mocking way. And then I thought, you know, that's really disrespectful. And this guy's gone to the trouble of trying to understand what might happen to his local community if we fracked in the Mendips. So one of the things that I've learned in the years that I've been doing this is you have to listen to what people are saying to you with respect and to try and understand where they're coming from, because they're coming from a very different place than you are. Another interesting question is, where do people get their data from? And this is the results of a study that we've not published yet, where we asked people who were experts in shale gas the same questions that were being asked in the YouGov poll that was being run by the University of Nottingham. And one of the questions was, do you associate shale gas with earthquakes? So this is just the data for that question. So at the time, and I'm sorry I've lost the stuff at the bottom, but I think this is around 2014, March 2014, the UK public, about 50% who said something said it was associated with earthquakes, and about 50% said it wasn't, but about a third of them said they didn't know. So what we then did was, before we gave a talk, we invited people to come to a talk, very much like this one, and before the talk we asked them to fill out a questionnaire to say where did they get their information from. And then after the talk we asked them the same question, said, have you changed your opinions after this talk? So these are the post-talk opinions. So what we find is that most of the people who left those talks had an idea of whether shale gas did or did not cause earthquakes, but actually it's another 50-50 split, which is really interesting. And depending on where people claim to get their information from, so we said, do you actively research in this? Is this your job? And people whose job it was, about a 50-50 split. People who had read reports, so not just reading the BBC webpage or their favourite newspaper webpage or watching the telly, actually going and reading, you know, the Royal Society or Royal Academy of Engineering report. Said slightly more. People said they do cause earthquakes. And people who said they got their information from the media, again, they said they were much more likely to say that it was associated with earthquakes. But let's unpick what that question actually means. Ooh, no, we won't, because it's not on the next slide. Later on, we will unpick what that question means. I have some quotes from what they were saying. But in a nutshell, the answer is, well, it depends what you mean by the word associated. So just about every media article says shale gas has been linked to earthquakes. So every media article says it has. But most of the earthquakes that are hitting the media in the US are nothing to do with fracking. They're to do with wastewater disposal from conventional oil and gas wells. So the people are picking up information from an incomplete sort of set of information. Right, so I'm going to focus the rest of this talk mainly on shale gas, because that's mainly where I had the slides prepared from previous talks, but I'll pop in and out of CCS and Radioactive Waste disposal. But I think it's worth just going through, where do these misconceptions come from? So this is a slide I use often to explain how fracking actually works. It's a cross-section. So this is distance horizontally in feet and depth beneath the surface in feet. And notice that it starts at 5,000 feet deep. And the black line here is the track of a well that's been drilled. Now, drillers can steer wells. It's absolutely fantastic technology. They have telemetry in the toe of the well that tells them where they are, and they can steer it to avoid obstacles. And they have things called logging while drilling. So the black lines here are the top and bottom of the target horizon that they're trying to get their well along to take that shale gas out. And if the well for some reason wandered up a bit, or the top of the shale wandered down a bit, and the driller could see almost in real time that instead of getting shale at the drill bit, they were getting whatever was on above, sandstone or limestone or something, so they could steer it back down again. So incredibly sophisticated engineering to push these wells down through the rocks. Then what you do to actually create a frac is you pack off an interval of the well. Packing off an interval basically means inflating a balloon, so that that segment of the well is isolated hydraulically from the rest. And then you perf the well, perforate it, you set off little explosive charges to turn a 10 centimetre diameter, centimetre thick piece of well casing into a colander that has holes in it. And then you put your fracking assembly in, you up the fluid and break the rock. Now breaking anything, break a stick, it makes a sound. Same is true for rocks. So these little green dots here, each one is a tiny earthquake that's happened when that fracture's popped open. And each of those tiny earthquakes has a magnitude about -2. And Mark Zobach, who this figure is taken from in the States, says -2 is about the same as dropping a gallon of orange juice on the floor. Now, Mark's much taller than me, but a US gallon is about 8 ounces smaller than a UK gallon, so it probably stands about the same if I drop some 2 gallons of milk on the floor, or a gallon of milk on the floor. Not very big, but we have sensors that can hear that, either from down the well or from observation wells nearby. And then, then you learn to use the slide thing. Then you do it again. You pull your assembly back, and you do another frac job, which are the pink triangles. Then you pull it back, and you do another one, which are the blue squares, and so on and so on. You do it from the toe to the heel of the well. And you do that to create a nice fracture network interconnected to your well that you can draw the gas out of. A couple of key things to note here is that none of those dots has gone further than a few feet above the target horizon. Now, if you think about the company, they are spending money like crazy to drill these wells and put these fluids down, pressurized fluids. The last thing in the world that they want is for those fracs to go zigzagging up to somewhere else. They'll lose circulation, they'll be pumping fluid into the overlying sandstone or limestone, which won't help them at all. And when they finish the fracking, drain the well, they might start producing water out of the sandstone instead of gas from the shale. So they monitor it as closely as they feel they need to, and to balance those risks. But in this example, the seismicity is very closely arranged around that well. So a lot of these cartoons that you see have these fractures that sort of zip up to the surface and contaminate groundwater. And this is an image from a paper by Fisher and Warpinski, who collated data from different shale basins in the US. This is data from the Marcellus Shale in the USA. And they just arranged them in depth of fracking. So these are the shallowest ones, these are the deepest ones. The red lines are the topmost dot, where the fracs extended up to, and the bottommost one. So you can see that the deep ones, this frac actually extended quite a long way up compared to these ones. Now again, look at the depths. These are in feet, and this is the height of Ben Nevis above sea level. The blue lines here are the depth to the nearest groundwater resource above that well. They're not directly above the frac, but in the kind of general region. And you see that there's almost the depth of Ben Nevis between the shallowest frac and the deepest groundwater. Now, a lot of people have said, well, Fisher and Warpinski would say that, wouldn't they? They work for the industry. But the fact is that getting hold of data where it's commercially sensitive is often best done by people who are in the industry. So, the evidence really is overwhelming that we're not going to frack all the way from top to bottom to top. One, because we're not seeing it, and two, because it would cost a lot of money to propagate a frac all that distance. And so people, even if you think they're bad people, they are actually out to make money from these frac sites. Another one is that fracking consumes huge amounts of water. And you see that a lot, huge amounts of water. But as I said at the start, if you're wearing clothes that are made of cotton, cotton consumes a huge amount of water. And this is a table from a report by the Groundwater Protection Council in the United States comparing the water use for different gas sources. So gallons of water per British thermal unit. And you see that actually shale gas is much lower than some other sources of gas and energy, nuclear energy. And in fact, the statistics that I remember most is that you can, for a 10-year run of a fracked well, typical fracked well, is equivalent to running a coal-fired power station, a 1,000-megawatt coal-fired power station for 12 hours. And it's equivalent to the amount that United Utilities loses in the northwest of England every hour. So if we're really worried about water, we need to do something about our sewage system and our water distribution networks. And beer. Anybody know how much water it takes to make a pint of beer? 11 litres. Oh. The world record is 7 for Coors make their beer with 7 litres of water. But, we use all the time in our industrial processes, in agriculture, in food processing, we use a lot of water. So if you were fracking in an area that was already water stressed, that would be a problem. but it would be the same amount of a problem as having a brewery in that area, or having very water-intensive crops, watermelons, which they grow in the desert in Libya and Utah. So is the controversy because people don't understand it? Well, I don't think it is, because there are some people who haven't taken the trouble to go and understand things. But when they take the trouble to sit and understand it, it's not that difficult. There's a lot of very good data out there and reports out there that can explain the technology quite simply. But if you explain it to people, a lot of them still say, well, they don't want it. So one of the other reasons is that people are uncertain about what it means for them. So, okay, you tell me that you can get it out safely and that you're not going to cause massive fracks that go up to groundwater, and you're not going to drain all my lakes in order to frack my local environment. What does it mean for my community? So this is a photograph from the air of Quadrilla's site in Lancashire during fracking. And the process of drilling a well means having a big truck-mounted drill, driven up, erected, maybe several truckloads of stuff to erect that. Before they do that, actually, they'll build a pad, it's called a hard standing, or a gravel pad. That pad will have to be bunded, meaning it's got a membrane underneath, like the stuff you put underneath gravel paths to stop dandelions coming up. And the idea of a bund is that if a spill happens, it's to stop any spills getting out into the soil. The process of drilling and fracking, as we said, it requires a lot of water, and it requires other chemicals. So they'll put chemicals into the water to help it move with less friction, or to help stop bugs growing in the well. And all of these involve truck movements. And so the fact is that when you're drilling and fracking a well, there will be quite a lot of trucks. And one of our undergraduates calculated this as being equivalent to one of those big out-of-town supermarkets. So one of those ones that sells school uniforms as well as potatoes. So imagine living next to one of those. You've got a nice country house, and somebody suddenly puts a Tesco Extra next to you. You're not going to be that happy about it. But that lasts for a few weeks. Afterwards, they do what this chap here has been to Witch Farm, so they put a nodding donkey on. They don't need to do that here. They put this type of structure on. This is it's called a Christmas tree. And it's the manifold on top of the Airth coalbed methane site near Falkirk. And that'll sit there quietly, buzzing away for 10 to 20 years, taking the gas out and pumping it to some kind of place where it will be cleaned up and then injected into the national grid. And after production, the regulations state that you have to put the site back. I read them. It was really interesting. So the frackers are required to, the soil that they move out here, they have to take it away, and they have to look after it for that 10 to 25 years and make sure that it doesn't grow giant hogweed or Japanese knotweed or any other invasive species. When they put the site back, they have to go underground, dig underground to beneath the level that any farmer is ever likely to have any kind of plough going in. And they saw off the top of the well. Well, first of all, they cement it closed, and then they saw off the top of the well with like a giant chainsaw. And then they bury it, and then they put the soil back that's free of Japanese knotweed, and it's not been trodden on, so it's not been compacted, and it will go back to being farmland. So that's the reality of what it will look like in the UK. There are lots of ways of making the impact smaller. So the truck traffic, you can avoid truck traffic by piping your water there. It's not commonly done in the US, but there's absolutely no reason why you couldn't do it and have pipes that bring the water onto the site. That will get rid of a lot of trucks. In the US, they're increasingly doing what's called factory drilling, where they'll have one well pad with lots and lots of fracked wells coming off that pad. So you have a lot of activity on one site, but it's concentrated in one site rather than being dotted around all over the place. And it's worth going through what the differences are between the US and the UK, because a lot of the concern has come from the US, where, quite frankly, some of the practices have been horrible. Really, some dreadful things have happened. One of the very common pictures you see on the media are these open pits of water that are on fire. Now, that's because the water that you take out of the well, you have to take the water out of the well to get the gas to flow out. And that's called flowback water, and it has gas in it. So if you chuck a match in or a lit cigarette, it'll go on fire. those are illegal underneath the EU Water Framework Directive. And whatever happens with Brexit, those laws are laws until we undo them. And I think we won't undo this one. It's a very sensible law because not only does it have methane in, but it has other dissolved organic chemicals that come out of solution like benzene and toluene and things that are carcinogenic. It's what you smell when you fill your car with petrol. And we know it's carcinogenic because Indian petrol pump attendants have much higher rates of cancer than British people who occasionally fill up their tanks rather than spend their careers filling up tanks of petrol. So we know that this stuff is nasty. And in the UK, we will have it in closed tanks that will be appropriately treated. The other image is flare stacks. Now, a site in the UK will have to have a flare stack. A flare stack is there as a health and safety fail-safe. So if something goes wrong with the well or some of the plumbing around the well and methane is released, that's an explosion hazard and it's a suffocation hazard for people on the site. So the wells will have to have a flare stack, but flaring is, again, it's not permitted except in emergencies. What's much better is to capture that gas and use it. So you can either use it on site to power generators on site, or you can just put it into the gas that you're sending off to the national grid. Now, again, that's product. So if you're venting methane up into the air or flaring it, you're not making money out of it. And we used to do this in the North Sea up until relatively recently. We flared all of the gas because we didn't know what to do with it. And then somebody invented the gas turbine power station, and lo and behold, there's money to be made out of that gas. So there'll be a flare stack there as an emergency fail-safe, in exactly the same way there'll be a defibrillator there in case somebody on site just happens to have a heart attack. But it is a health and safety thing. In the US, there's this concept of green completions, which means a suite of technologies to make fracking less environmentally damaging. We don't really have that concept in the UK because that's what we have to do by the regulations. And the Environment Agency have prepared a best practice guidance in what should we do in order to minimise that. The other two on here, Halliburton exemption. The US onshore oil and gas industry were exempted from the Clean Water Act by an outgoing Vice President, Dick Cheney, who worked for Halliburton. And most of the big oil companies see this as a really bad thing, because actually the big oil companies can afford clean, safe, well-managed sites. It's the one man and his dog guys with a drill rig that don't have the kind of resources to run those sites as cleanly. And those are often the places where problems have happened. But we have the EU Water Framework Directive and a whole bunch of other legislation that will stop it will regulate practices that might damage surface water and groundwater. They won't stop it because accidents happen. Like I say, the JOLSOC will have had people tripping over and hurting themselves. Where you have people, accidents happen, but regulation is about trying to stop that or minimise it. The other mistake that was made in the States was the idea that companies wanted to keep it commercially confidential. They didn't want to tell you what was in their frac fluid, the same way Coke didn't want to tell you what was in Coke for a very long time. The companies in the US now realise that was a PR disaster because it makes it sound like you've got something to hide. And I don't know if you remember the days when people said Coca-Cola's got cocaine in it. You know, little kids are like, oh, get high, drink Coke. You know, you can't. It doesn't have cocaine in it. It's illegal. But not telling people what is in it just drives that public fear. I'm going to skip that. So interestingly, Chris Ford, this PhD student of mine, has been looking at the planning objections to shale gas developments. And I've circled in red here the interesting numbers. So there's 5 shale gas developments here that have come, the applications have gone in between June 2014 and May 2016. And you can see over 19,000 objections to one of the ones in Lancashire and nearly over 14,000 objections to the other one. But the numbers of objections are going down. And Chris is also looking at where they've come from. And in his previous incarnation, before he became my PhD student, he was a town planner. And he said, sometimes we get 19,000 objections. It's not unheard of. But what is unheard of is that these objections weren't from the people who were going to be materially affected in a planning sense. So Around 50% of those objections came from more than 5 kilometres away from the sites. And Chris has chosen that radius because he thinks that's the location where people are likely to be affected by the truck traffic, the drilling noise, the lights, because they'll have lights on the site. They'll drill and they'll frack 24/7. So there's light pollution, there might be dust. But those are the communities within a very tightly constrained area. And for these planning applications, they're getting objections from a really large distance. And one of the reasons is that the NGOs, the anti-fracking NGOs, have organised and really drummed up support for their cause, but also because the objections are not just on the basis of it's going to cause damage to groundwater or it's going to have trucks going outside my scout hut. The big objections are around climate change. And there's this movement to keep it in the ground. Let's not use more fossil fuels. We cannot afford to burn all of those fossil fuels. And so interestingly, these planning applications, what he hasn't done yet is look at the correlation between what they're objecting to and how far away they came from. And a lot of these are kind of form letters that people have signed that have the same stuff on. But certainly through time, he's not completed the proper study, but just from skim reading the applications, he gets the sense that there's been a bit of a change in what people are objecting to. So people were very worried about seismicity early doors, but it's fairly easy to explain that you're never going to make big earthquakes from fracking. Wastewater disposal, yes, and I haven't got time to explain that now, but it's fairly easy to reassure people that we understand how to deal with nasty toxic stuff. We do it on a day-to-day basis in industrial sites across the UK. But climate change and this leave it in the ground agenda has not gone away. Public health issues is a really interesting one. It's really, really difficult to prove a health causation between things. Remember how long it took them to convince everybody that smoking caused lung cancer? And, there was a story there about the tobacco companies maybe seeding things, being disingenuous. But actually, it's very, very difficult. And there's good studies in the States that show a spatial correlation between frack sites and various different problems. But the academics who publish these studies, if you read their the discussion at the end of their papers, they say, this is a study on the statistical correlations, it's not a study on the causes. But we can speculate the causes. And one of the common speculations is it's those open pits full of water that are causing low birth weight babies in Colorado or cardiopulmonary disease. Those won't be allowed here. So maybe we would get rid of that problem entirely, or maybe not. Maybe there are other pathways that we've not examined. And there's a huge amount of research going on in UK and other academic institutions trying to understand what are the pathways for potential pollutants getting out of these types of facility into people. But Chris has found that recent applications do seem to have shifted. And I've been giving talks about shale gas now for 5 years or so, and I really love earthquakes. I think they're so cool, but they're so irrelevant to fracking. And what I always end up with these talks is saying, actually, the real risks, there's the climate change one about fossil fuels, which is a political decision. It's not a problem of a particular well. It's a political decision about how do we run our energy system. But the real risks that somebody gets run over by a frack truck, road traffic accidents. It could be an operator on the site. It could be a kid coming out the local scout hut. It's noise and visual amenity and the stress that introduces to people's life, and other sort of low-grade, not very exciting, not very Hollywood environmental effects. Oh, here's the answer about the questions. Does it cause earthquake or not? And the reason it's 50-50 is that some people say, yes, it does, but they're tiny, and the other 50% says, no, it doesn't, but it does cause microseismicity, which is exactly the same thing. How long have I got?
5 minutes.
5 minutes. I'm way behind on my slides. So, fairness matters. I've just been I'm now head of department, and I'm realising that the perception of unfairness causes so much more angst than actually, when I didn't try to deal with workload management, people weren't as grumpy. But this is a classic quote from a Tory peer that fracking, we'll just do it in the desolate northwest, there's nothing there. And then he got prodded about it and he changed his mind and said, well, we'll do it in the northeast. Wasn't a good idea. But there's another issue about fairness, which is that we are importing shale gas. So this is the shale gas for manufacturing ship that INEOS had coming up the Forth River last year. It's bringing ethane from US shale gas fields to the Grangemouth refinery, which is making plastics, it's making pills, it's making stents for heart patients, it's making your glasses, it's making your buttons. It's not, it's making the feedstock for those. And I found this article yesterday that the US, the first American imports of US liquefied natural gas from US shale fields, or from American shale fields, has just started arriving in the UK. It's not coming from America, it's coming from the Dominican Republic and Peru. So if we're really worried about these environmental effects, then by this happening, we're offshoring that. So this really is NIMBYism. This is, I don't want the British countryside to be spoiled by fracking, but I'm quite happy for the Dominican Republic to put up with it. So we live in this incredibly connected world. And unless we face up to the consequences of how we consume, then we're really pushing the problem away to somebody else. So where and who are these impacts happening to? This is a figure originally from an American group led by Adgate that talks about this idea that there are local site impacts and there are regional impacts. So traffic will, in a rural area, truck traffic could churn up a narrow network for quite a while, quite an area. And there are global impacts such as climate change. But there are also benefits. So there'll be money coming into the community. Now, some of that will come in through the fact that the frackers will need a B&B. Some of it will come in through community benefit schemes, which the UK industry has committed to 1% of all profits going to communities, and INEOS have committed to 6%. I'm not sure those numbers are exactly correct. I didn't check them, but they certainly were correct a year or so ago. There may be benefits from climate change. The US is the only country in the world that's met its Kyoto Treaty targets, despite not having signed the Kyoto Treaty. And the reason for that is that US shale gas has pushed coal out of the energy mix. So US is closing coal-fired power stations and opening gas-fired power stations. That's got a climate change effect, a very immediate one. Coal is a dirty way of making electricity. So, but those benefits are distributed in a different spatial way. So that will cause public unrest. If you think, well, I'm taking all the hassle here, I'm the one with the trucks, and I'm not getting the benefits, I'm not seeing the tax dollar coming into my community, that's not fair. In the interest of time, I'm going to skip through. Trust. Trust is a really big one. And this was the editorial in the British Medical Journal shortly after Public Health England published a report into health impacts, and which basically said, in all likelihood, we can get shale gas out of the ground without any major public health impacts, provided it's regulated properly. And the bit underneath the BMJ was mistaking best practice for actual practice. And of course, doctors in A&E see car crash victims every day. We know it is possible to drive a car safely. You wear a seatbelt, you do all the rest of the things, but car crashes happen and they get carted off to A&E. So the doctors know this. They know that industrial accidents happen. Big chemical facilities have all these procedures in place to stop people getting burnt or falling off high towers or whatever. But they happen. It's why we have the Environment Agency and Scottish Environmental Protection Agency, because we need to regulate these things to try and stop them happening. So there's a big issue of trust. Do the public trust that those companies have their interests at heart? Oh, I threw this in. I know I'm running out of time, but I love this paper. And I don't know if the Geosoc's seen this before, but this was a study of 222 Hollywood movies and the scientists in them. If you're a physicist, you're most likely to be mad. But if you're a geologist, you're most likely to be good. So there's a list there of the type of scientists that are mad and bad and the type of scientists that are good. But interestingly, geologists were naive as well. So if you think that chap in Jurassic Park, he was so, we're going to have these dinosaurs, and then he was totally exploited by the evil, what's-his-face, Attenborough. So another really interesting thing about trust is about where you get your information from. And this paper is not about geological engineering, but it is about energy industries and about genuine harm that happens to people. So if an NGO comes to you and says, this thing that's happening near your house, it's going to be awful. It's going to destroy your community, it's going to pollute your water, it's going to poison your children, that causes you stress. And this is a study, an epidemiological study of something called wind farm syndrome. So there are people who believe that wind farms make them sick. Now, there has not been a physiological link found between flicker and low-frequency noise and the symptoms that people are exhibiting. But this guy went around and looked at where that wind farm syndrome is occurring. And it was occurring where the NGOs were holding protests. So what was making people sick was probably the stress and anxiety of those protests, not the wind turbines. So there's a bit of thinking there about where do you get your information from? How much do you trust that information? And do you trust, whose best interest does the person have who's giving you that information? I'm going to skip these next two. And the final thing is framing. Now, framing is a social science thing that says, let's put this in context. And I see on your link, your reading list, you've got a link to something that I wrote, a blog that I wrote with an economist at Strathclyde about the Scottish Government consultation on fracking. Now, if you ask people, do you want fracking? A lot of them say no. All right, then, okay. But do you want nuclear energy? No, not that either. Okay, do you want wind turbines? No, they're ugly. Kill birds. Or do you want coal? No, it's really bad for the environment. It gives people asthma. Well, what do you want? So a much better and much more interesting question is, how do we get the resources that we need? Rather than, do you want a big mine next to you to get neodymium? Or all our neodymium comes from China. And we need neodymium to make magnets for wind turbines. But we might be able to get some out of Greenland, pristine wilderness. Should we get it out there? That's a very different question than should we dig up Greenland? So this is a report that's really worth reading. The Royal Society of Edinburgh, Options for Scotland's Gas Future. They looked at Scotland will need gas. Even if we meet all our incredibly ambitious climate change targets, they're much more ambitious than the UK's. We will still need gas. And I can't remember the amount of gas we need, but we will need it for heating homes, for bits of electricity we can't otherwise manage, for transport, and for petrochemicals. So the panel looked at demand reduction, importing gas, onshore gas, and offshore gas. And the one that came out tops was demand reduction, right? If we just use less gas, if we insulate our homes properly, that's fine, but it costs a lot of money, and it's really difficult to do. And it's okay if you're a dictator and say, right, you all have to wear more jumpers, but try getting re-elected if you're going to force everyone to turn their heating down. Importing gas, well, that's offshoring the problems again, isn't it? And at the moment, we get some imported gas from... we don't get much imported gas in Scotland, but in England we do. The majority of that comes from the Norwegian North Sea. Some of that comes through an interconnector from Northern Europe. But increasingly, we're bringing liquefied natural gas in from Qatar. And Eastern Europe is getting piped gas from Russia. And are we comfortable that Qatar and Russia have the same environmental and health and safety legislation that we do to protect workers in those countries and to protect the environment in those countries? So one solution is this, and this is an incredibly complicated picture, but I can't encourage you enough to go to this webpage. The web address is at the top. It's a calculator. It lets you be boss. It lets you be the king or queen of Britain's energy system. And you can turn on and off things. You can turn up the nuclear power stations, turn up offshore wind. You can force everybody to electrify their home heating systems and get rid of gas central heating. And every time you click one of these buttons, it recalculates the overall energy demand, where that supply is coming from, and how close we are to our climate change targets. And it's fascinating because it's really difficult to do. But this is the kind of tool that gets people thinking about the whole mix, the whole energy mix. So I think I'll make this my last slide. I've taken on a bit of a journey through slightly, with fewer slides, but a bit of a journey through what I think are the big objections, the big reasons that people are feeling uncomfortable about these geoenergy subsurface activities, shall we say. And community acceptance matters. It can kill things. It can stop things from happening. And it matters directly because If too many protesters chain themselves to something, then at some point the company's just going to walk away and say, we can't do this anymore. They're very bloody minded. Am I allowed to say that? They're stubborn. They're not going to walk away easily. But if the sunk cost in dealing with the security for protesters is too large, it doesn't make any economic sense. But it also indirectly affects the political climate. So we currently have a moratorium in Scotland because the Scottish Government have said they're going to take an evidence-based approach to understanding what's going on. But I bet if people were knocking down the doors of Scottish Parliament going, we want cheap gas, then they might have made a different decision. It's no longer legitimate for organisations, I say organisations, not companies, because some of these are publicly owned organisations. Scottish Water, that are drilling that tunnel in my neck of the woods, is a nationalised organisation. But it's not acceptable anymore to just say, right, we're going to do this. Right, we're going to put HS2 here. We're not going to consult on it. We're not going to talk to the people, the wildlife people or the air quality people, or we're just going to put it there. That doesn't happen anymore. And this process of consultation is really, really important. If you don't do it, or you don't do it well, then you lose what's called the social licence to operate. Whee! Social licence to operate isn't a real thing. It's not a piece of paper, but it's a sort of nebulous thing that if you've got the social licence to operate, people are like, you know what, it's a bit annoying that junction at Crossmalouf train station has been shut for 6 months, but we're going to get a good sewage tunnel out of it, and I trust you. I think you have the same values as I do. You're going to look after the environment and make sure that Glasgow is a safer place, less flooding. That's a social licence. And it costs a lot of money and time to get it, and one or two bad things in the press can lose it. So I'm going to finish there. I'm slightly over time, but thank you very much.
Thank you very much, Zoe. Questions?
It's just interesting how we've become more environmentally aware, because in southwest Scotland they used to have this nuclear power station called Chapel Cross, and it used to just have a low-level waste pipe just sort of going straight out into the Solway Firth, and it was mixed with the raw sewage from the nearby sewage farm, and happily doing its business into the water for the sort of since it was built in the mid-50s to sort of the 90s, I think, and nobody really batted an eyelid, and it's just now that everything is all much more aware. So is that what's happening now? Is everybody aware of any sort of minor thing that could affect the ecosystem?
I wouldn't say everyone's aware of every minor thing, but I think in general there's more of an awareness about how we're all part of a linked system. And it's really interesting. My kids at primary school are getting this at school. I never got it at primary school. We did Romans and slavery. But we are part of a linked system, and if we do something in one place, it has an effect elsewhere. I can't comment on Chapel Cross, but I will say that the British nuclear industry has got an almost unparalleled record of health and safety. And in fact, the nuclear industry as a whole has killed far less people per gigawatt hour than any other type of electricity generation. So the worst is coal. So 10,000 coal miners a year die in China. Nuclear has the best safety record per gigawatt hour. Now, there are disasters, and they're really high profile, but the other industries have small little disasters all the time. US coal transport is really dangerous, a lot of crashes in trains. So it's slightly giving you two answers to two different points, one about safety and one about are people more aware. But people are definitely more aware, and we should be. We live on a finite planet, and we've got to give it on to our kids and grandkids.
Questions, gentlemen?
Early on in your talk, you referred to the public perception of risk, which is extremely uncertain. Understanding of probability is not widespread. But it seems to me that there are aspects of fracking where there are uncertainties, and the picture you've presented is perhaps showing a consensus of geological opinion, but there are uncertainties. I mean, I mentioned a couple of things. There are shale gas sites in Scotland, but Professor John Underhill recently produced a paper saying that they would not be productive for various important geological reasons, and the same applies to much of the rest of the UK. So that's an element of uncertainty. Is there or isn't there a resource there that's useful? The other is that there is a common assertion that putting water containing lots of toxic chemicals down these wells, that stuff will stay there. I mean, the stuff that we don't pull out again, the stuff will stay there and not mix with groundwater. But there's an awful lot about the circulation of water that we do not understand as geologists. There's a lot of uncertainty. And I haven't ever seen any estimate of the likelihood or the risks associated with that material getting into groundwater supplies that we use for drinking.
Okay, two excellent questions. So I'll start with John Underhill's paper. Many of you will have seen the headlines saying that we're 55 million years too late. Now,